If you go to the early universe right after the Big Bang, it was expanding way faster than the speed of light. Just like how Copernicus presented the heliocentric model, we may be in for another mind-blowing revision to our cosmic understanding. A debate has arisen in cosmology known as the crisis of cosmology. Neil deGrasse Tyson has said that the James Webb findings have ended this debate with a physics-shattering image. So what exactly is this crisis, and how has the James Webb Space Telescope contributed towards it? Old-timers might find it hard to call it a crisis, yet it truly is, particularly when we once didn't know the age or size of the universe because these parameters were only understood within a factor of 2. Join us as we venture into the very frontier of science where our knowledge is constantly put into question and where we're making unanticipated discoveries. Over the past century, a significant achievement in cosmology has been the establishment of a standard model outlining the universe's history and its current state. Gravity, guided by general relativity, primarily dictates the universe's evolution, explaining both its expansion and the formation of large cosmic structures. The known components include dark energy, dark matter, normal matter, neutrinos, and photons. The universe originated from the hot Big Bang around 13.8 billion years ago, preceded by cosmic inflation which caused density imperfections. But what if we told you that this very model is now under scrutiny? This model has been responsible for our understanding of the universe for the past century or so. But despite extensive observational support, this model might be incomplete. While we're getting more and more observations, each new one has to be examined in the context of the model to see if it still holds up. Astronomers have gained a new tool in their toolkit with the JWST, and this device has been creating problems in our standard model. It all started in the early universe before stars or galaxies emerged. Neutral atoms were forming around 380,000 years post-Big Bang. Then, 550 million years later, reionization occurs, during which most of the universe becomes ionized. The initial waves of reionization started approximately 200 million years after the Big Bang, with some stars possibly forming 50 to 100 million years after. The JWST, with its capabilities, allows astronomers to unveil more distant galaxies than previously possible, offering new insights into the early universe. First, let's go through what we know. The standard model of cosmology, known as the inflationary hot Big Bang or lambda CDM, has been remarkably successful in explaining various features of the universe. This includes gravitational lensing, the cosmic web structure and growth, the internal motions of galaxies, their relative motions within groups and clusters, and features in the cosmic microwave background. This model predicts that as we look further back in time and cosmic distances increase, the observed galaxies should be inherently smaller, bluer, less developed, and less rich in heavy elements. At some point beyond our current observational reach, we anticipate entering the universe's dark ages, devoid of visible stars or galaxies. But while verifying the integrity of these explanations, scientists have found conflicting evidence, resulting in a crisis of cosmology. The cosmology crisis is simple. We don't really know the age of the universe. Different methods give different results, and it's up to cosmologists to find out why, but they're struggling to do so. Let's take a look at the methods we use to measure the universe's age. The first one is cosmic background radiation. To unravel this cosmic mystery, scientists delve into the universe's expansion history, and to do that, they need mathematical modeling. This mathematical modeling is Einstein's general relativity theory. Applying this theory to the entire universe produces the Friedmann equations, linking the universe's composition, dark matter, dark energy, radiation, and more, with its expansion rate at specific times. By measuring these contents, we can get the age of the universe, and we can use the cosmic microwave background to do just that. The cosmic microwave background is the light from the early days of the universe back when it was about 380,000 years old. It is a crucial tool in measuring the universe's contents. Exceptionally detailed maps of the CMB provide insights into the universe's composition. One such map is from the European Space Agency's Planck mission. But there's an issue with these maps. They lack data on dark energy, which is a significant player in the current universe. Dark energy didn't influence the early universe, so scientists must incorporate its effects manually based on other observations. Despite this, Scientists can use the Friedmann equations to figure out the expansion rate of the universe at any point in time. They can even figure out the expansion rate today, and through that, they can also determine the age of the universe. Another way to measure the age of the universe is to look at exploding stars. While the cosmic microwave background provides a thorough record of the universe's makeup, it's a historical snapshot originating billions of years ago. Another way to measure the universe's expansion is by directly observing its rate of growth. This is done thanks to type Ia supernovae, a celestial spectacle where a star dumps its atmosphere onto a nearby white dwarf, the remnants of a deceased star. When the white dwarf hits a critical mass, it erupts into a supernova. Since this cosmic drama unfolds similarly across the universe, scientists consider supernovae as consistent benchmarks or standard candles. This means we know their expected brightness, and by comparing it to their observed brightness, we can estimate the universe's expansion rate at the time of the supernova. This method, employed in the late 1990s, played a pivotal role in discovering dark energy, becoming a cornerstone in cosmological measurements. It's particularly useful for determining the Hubble constant, a measure of the universe's expansion rate, even though it's not precisely constant. The Hubble constant is the yardstick for charting the universe's expansion since the Big Bang, about 13.8 billion years ago. NASA has pointed out something interesting here. It's not just the expansion rate, but the implications of this rate. If expansion slows, it suggests an unknown force, possibly dark matter, influencing the deceleration. On the other hand, if the expansion rate speeds up, it could be that dark energy is speeding up the growth. Scientists found something interesting in January 2018, though various telescopes indicated that the universe's expansion rate varies by observation point. The Hubble Space Telescope and Gaia Space Telescope measured a faster expansion of 45.6 kilometers per second per megaparsec in the nearby universe. In contrast, the Planck telescope gauged a slightly slower expansion of 41.6 kilometers per second per megaparsec in the more distant background universe. A megaparsec, equivalent to about 3.3 million light-years, represents an unimaginably vast distance. Edwin Hubble, the namesake of the Hubble Space Telescope, first proposed the expansion rate. Hubble, an American astronomer, focused on studying galaxies, especially those distant from us. In 1929, prompted by astronomer Harlow Shapley's observation that galaxies appeared to move away from the Milky Way, Hubble deduced that the farther galaxies were, the faster they seemed to move. Initially interpreted as galaxies drifting apart, astronomers now understand this as the universe's expansion. Regardless of your cosmic location, you'd witness the same phenomenon at the same speed. Hubble's initial calculations based on limited data have evolved with technological advancements. Telescopes like Hubble and Gaia observe Cepheid variables and refine measurements. Other telescopes utilize CMB readings to calculate the constant. However, the method has limitations. The availability of supernovae for distant observation is scarce, restricting our view of the remote universe. Nevertheless, in the 20 years since dark energy's discovery, scientists have been stumped. The issue is that the measurements from these two approaches are not consistent. These two points of view disagree on the age of the universe and the rate of expansion. This is because, while measurement technology has gotten more accurate over time, minor variations have also emerged. The development of more advanced technology is motivated by the desire to answer our questions once and for all, but ironically, these advancements end up producing more questions in the process. However, the change is marginal. Only 10 to 20 million years separate the estimates. When you consider the fact that the universe is 13.77 billion years old, it's a small amount, but it's still worth looking into. So how do we explain such a discrepancy? One solution proposes flaws in our CMB measurements. Yet the Planck CMB measurements, among the most precise in science, have undergone extensive testing since their 2013 release, validating their accuracy. An alternative perspective suggests a potential gap in our understanding of dark energy. Perhaps dark energy varies over time, intertwines with dark matter, or involves another unknown factor. This possibility captivates theorists, sparking numerous exploratory papers. Lastly, the accuracy of supernova measurements could be questioned. Although more directly gauging the present expansion rate, supernova observations are not foolproof due to the complexity of exploding stars. If we don't completely comprehend the intricate physics, supernovae can't serve as a precise cosmological tool. A touch of uncertainty in supernova modeling could resolve the entire discrepancy. The JWST added to the crisis, but there isn't just one crisis in cosmology. The JWST further complicated things. According to Neil deGrasse Tyson, the JWST has found things that, to our current understanding of the universe, shouldn't exist. Something had to change. Our current scientific understanding needs to be reworked, but we simply have no idea where to start. Regardless, the JWST's discoveries continue to push the boundaries of our cosmic knowledge. The implications of these findings are profound and may lead to significant revisions in our understanding of the early universe. One possibility is that the processes that led to the formation of massive galaxies were more efficient or occurred differently than our current models predict. For instance, it may be that the formation of stars and galaxies happened on a much shorter timescale than previously thought, or that the conditions in the early universe were more conducive to rapid galaxy growth than we have understood. Additionally, the unexpected size and development of these early galaxies might suggest that our models of cosmic evolution need adjustment. This could involve reevaluating the role of dark matter and dark energy in galaxy formation, or reconsidering the mechanisms of gravitational influence and structure formation in the nascent universe. The JWST's ability to observe these distant and ancient galaxies with unprecedented detail is crucial for testing and refining these models. As we continue to analyze the data from the JWST and other observatories, scientists will need to address these challenges head-on. Future research will likely focus on reconciling the discrepancies between observed galaxy sizes and the predictions of the Lambda CDM model. This might involve developing new theoretical frameworks or improving our understanding of cosmic phenomena that were previously poorly constrained. In summary, while the JWST has indeed added complexity to our cosmological models, it also represents a powerful tool for advancing our knowledge of the universe. The discoveries it has made challenge existing theories and open up new avenues for exploration. As we delve deeper into these findings, we may uncover more about the universe's infancy and the fundamental processes that shaped its evolution. The ongoing analysis of JWST data promises to be a pivotal chapter in the quest to understand the cosmos. The challenges presented by the JWST's findings underscore a pivotal moment in cosmology, as our models must adapt to new evidence that could reshape our understanding of the universe. One key area of focus is the nature of early galaxy formation. Traditional models, including the Lambda CDM model, posit a gradual buildup of structure over billions of years, driven by dark matter and dark energy. However, the discovery of exceptionally large and well-developed galaxies in the early universe suggests that galaxy formation might have occurred on a much faster timescale than previously thought. This revelation prompts questions about the physical processes involved in galaxy formation. One hypothesis is that the early universe may have experienced rapid star formation episodes or contained unusually high concentrations of primordial gas, facilitating quicker galaxy growth. Another possibility is that interactions between galaxies and their environments in the early universe were more dynamic than current models account for. These interactions could have accelerated the formation of massive galaxies through processes like galactic mergers or inflows of material from surrounding regions. Moreover, these findings could imply that our understanding of dark matter's role needs refinement. Dark matter, which interacts primarily through gravity, has been thought to provide the scaffolding for galaxy formation. However, if galaxies were forming more rapidly or differently than expected, it might suggest that dark matter's influence is more complex than previously understood. For instance, variations in dark matter density or its interaction with other cosmic components might have played a role in shaping the early universe's structure. The role of dark energy, which affects the expansion rate of the universe, is also under scrutiny. If early galaxies formed differently from what the Lambda CDM model predicts, it might indicate that dark energy's influence varied over cosmic timescales or interacted with dark matter in ways we have not yet fully explored. Adjustments to the theoretical framework may be necessary to account for these potential variations and integrate them into a coherent model of cosmic evolution. In addition to these theoretical implications, the JWST's discoveries could have practical impacts on observational cosmology. For instance, the telescope's ability to detect faint and distant galaxies provides a new vantage point for studying the universe's earliest epochs. Future observations might reveal even more about the formation and evolution of these early structures, offering further insights into their nature and development. The detailed data collected by the JWST could refine our estimates of cosmic parameters such as galaxy masses, formation rates, and the distribution of dark matter. As astronomers and cosmologists work to incorporate these findings into existing models, collaboration across the scientific community will be crucial. By combining data from the JWST with observations from other telescopes and theoretical advancements, researchers can develop a more comprehensive picture of the universe's early stages. This collaborative effort will help address the current discrepancies and refine our understanding of how galaxies and cosmic structures came into being. Additionally, these developments highlight the importance of maintaining a flexible approach in science. Theories and models are continually tested and revised as new data emerges, reflecting the dynamic nature of scientific inquiry. The JWST's contributions exemplify how groundbreaking discoveries can challenge established views and drive progress in our quest to comprehend the universe. Ultimately, the quest to reconcile these new findings with our theoretical models will likely lead to profound advancements in cosmology. The insights gained from the JWST's observations are not just about correcting existing theories, but also about exploring new possibilities in our understanding of the cosmos. As researchers continue to analyze the data and develop new models, the journey of discovery will likely reveal even more about the universe's origins and its evolving nature.